So in the last video we built a A-stable circuit with the 555 timer for the clock module for the 16-bit computer I'm building, but we might want to be able to manually step through a program by pushing a button or something like that. So I can hook up a button and then tie the input of the button high while pulling down the output, so that when you push it the output gets connected to 5 volts, but otherwise it's connected directly to ground with a 1k resistor. And I'll also hook up a LED to the output with a 220 ohm current limiting resistor for it, just so we can look at the output. So now we have a button that's normally pulled down, but when I'm pushing it, it's tied high. And so this is the circuit we have right now. We have 5 volts connected to one side of the button, and then the 1k resistor pulling it down on the other side, and then we have our LED and current limiting resistor connected to ground from this side. And so this is a part that you push with the button. You push this down and it connects these two contacts. So you'll push it down like this, and then as soon as you let go, it will go back to normal. But when you press the button, there's a good chance that it can bounce off the contacts and then onto them, and then maybe bounce off and on a couple times. And so what this will look like is it will go on, then it'll bounce off, and then it'll bounce on again, and then when you let your finger go, it'll go down, or it might bounce on and off a couple times. So what you're going to see here is 2 clock pulses, and that's definitely not what you want if you want to step through a program step by step. And so we can actually look at this happening on the oscilloscope. So I'll keep pressing the button until I find a pulse that bounces. Oh, and there's one. So if I zoom in, you can't see the rising edge of the first pulse, but you can see that it's bounced off and then it's bounced back on. And so this is all a problem that can be fixed with the 555 timer. So I've got a monostable set up, the 555 timer this time, so I'll run over what's on the outside of it. And if you want to know more about what's on the inside, the last video I did on the A-stable 555 timer, I explained it all. And so pin 1 is connected to ground, pin 2 is connected to the output of this button, which is normally pulled up, but when it's pressed it's tied low. Pin 6s and 7 are tied to each other. Pin 6 is connected directly to a 0.01 microfarad capacitor, which is then connected to ground, and pin 7 is connected to a 1 mega ohm resistor, which is then connected to 5 volts. And then pin 3 just has a LED with a current limiting resistor that's connected to ground. Pin 5 is there should be a capacitor connecting that to ground. Actually, I'll change that. So pin 5 is connected to a 0.01 microfarad capacitor, which is then connected to ground just like we had with the A-stable setup. And pin 4 is connected to 5 volts just like we had in the A-stable setup. So first I'll say what this circuit actually does. So when this button is pushed, this output turns on for a certain amount of time depending on the value of this capacitor connected to pin 6 and the resistor connected to pin 7. And even if you press it more than once while the output is still high, you'll only get 1 clock pulse from it. So now I'll give a rundown of how this works. So you just powered it on, and Q is going to be low. So what that means is not Q for the SR latch is going to be high. So this path from the collector to the emitter is going to be closed, so current can flow through there. That means that current's going to flow from pin 7, because that's directly connected to 5 volts, through the collector out the emitter to ground. And if this capacitor was charged, it could discharge through the collector and out the emitter, but it's not charged because we just powered it on. So current's going to be flowing to the base, and then you're going to have current flowing from pin 7 into the collector and out the emitter. And just remember that if the capacitor was charged, it would be discharging, but it's not charged, so it's not going to be discharging. So let's look at what's being inputted into this comparator in particular. So at the positive input, you're always going to have 1.67 volts because it's tied to this voltage divider. At the negative input, it's being pulled up with this 1 kilo ohm resistor. So at the moment it's 5 volts, which isn't less than 1.67, so the set's going to be low and there's not going to be any current flowing, so it's not going to set the Q. But as soon as you push this button, it's going to be tied directly to ground, and you're going to have 0 volts here. And of course 0 volts is larger than 1.67 volts. So this comparator is going to go high at the output, and it's going to make this set go high. And when the set goes high, it's going to set Q, and it's going to turn this LED on. And now, of course, because Q is on, not Q has to be off. So you're not going to have any current flowing to the base, and it's not going to be pulling current from this 5 volts. So now the only place for this 5 volts to go is to charge up, oh, wrong color, is to charge up through here and charge this capacitor, because that's the only path to ground it has at the moment. So this capacitor is going to charge up like that. So the capacitor is charging up, and even if you let go while the capacitor is charging up, it's not going to do anything. This comparator is going to go low, but it's already set in, so it won't actually do anything. So this capacitor is going to be charging up whether or not this button is closed or open. So this capacitor is directly connected to pin 6, which is connected to the positive input of this comparator. So as the voltage here for the capacitor is rising, the input here is going to be rising, and it's going to be rising, and as soon as it goes above 3.33 volts, this comparator, the output for the comparator, is going to go high. Now that's going to reset the latch. So assuming you've taken your finger off the button now, there's going to be no current flowing through here. It's going to reset the latch. Not going to have current flowing here. These LEDs going to turn off, and this not Q is going to go high. You're going to see it's pulling 5 volts from pin 7 here like it was before, but now this capacitor is going to be discharging like that. The capacitor is going to be discharging, and it's going to really quickly discharge like that, almost instantly. Of course it's not going to instantly discharge, but it'll look like it's instantly discharged because there's barely any resistance to ground, so it's going to very quickly discharge. This positive input for the comparator is going to be at 0 volts, so you're not going to have current flowing here anymore, but that doesn't matter because the not Q is already set high, so whether or not you have current flowing to the reset or not, the not Q is already set high until you press the button again. And so what that's going to look like for the output is, I'll do it in green, you're going to have the output low. As soon as you press the button, the output's going to go high. It's going to stay high until this capacitor reaches 3.33 volts. Then it's instantly going to drop low, and it's going to continue like that until you press the button again. And so you can see, the longer this capacitor takes to charge up, the longer pulse width you're going to get. So the larger the capacitor and the larger the resistor, because if the resistor's larger, it'll take more time for the capacitor charge through it. So the larger the capacitor and resistor, the longer pulse width you're going to get. And so no matter how many times you push the button while it's high, it's only going to pulse once. No matter how many times you push it in between this area, it's only going to pulse once. So that means even if this button bounces, this is only going to pulse once. And so this is why this is such a helpful circuit when we're trying to build a debouncing circuit, is what this is called. So now I can build this on a breadboard, so I'll get rid of all of the stuff for the button we had just before, but I can keep the actual button on the breadboard. So I'll start off by adding a pull-up resistor to the output of the button, and then I'll tie the input of the button low. I'll plug in the 555 timer. I'll connect 5 volts to pin 8 and ground to pin 1. Now I'll connect the output of the button to pin 2 of the 555 timer, and I'll connect pin 4 to 5 volts. Now I can connect the 1 mega ohm resistor from 5 volts to pin 7, and for now I'll just connect the 1 microfarad capacitor from ground to pin 6 so we can actually visualize the LED staying on. And now I'll connect pin 6 and 7 together. I'll connect an LED to the output of the 555 timer, and then put a 220 ohm current limiting resistor from the LED to ground. Lastly, I'll connect a 0.01 microfarad capacitor from ground to pin 5. So I got power plugged in, and you can see when I press a button the output stays on for longer than I push the button for. And the way you figure out how long the output stays on for is by multiplying the resistance in mega ohms by the capacitance in microfarads, and then multiply that by 1.1, and that gives you how long the output will stay on in seconds. So it's staying on for around 1 second. Not quite, but that's just due to the tolerances on all the components I'm using. So now I've shown you guys it actually works. I can replace a 1 microfarad capacitor with the 0.01 microfarad capacitor. And now you can see the pulse is a lot shorter. Now I'll show you guys what all this looks like on the oscilloscope. So I'll press a button, and the blue line is the capacitor voltage and the yellow is the output, and you can see that as soon as the capacitor starts charging up, the output goes high, and as soon as it discharges, the output goes low, which is exactly what we predicted just before. So now I'm going to build this circuit on Easy EDA. So I got basically everything I need already here from the A-stable circuit I built last time, so I can just duplicate a lot of stuff here except for the button. So I place that down. I'll duplicate the 555 timer, and I'm gonna need a couple of resistors, so got them out. I'll put the 555 timer in a good spot. Move that out of the way. I'm gonna need 2 of these ceramic disc capacitors. I'm gonna need another LED, and so I'm pretty sure that's all I'm gonna need. So I'll hook everything up. I'll start off by connecting 5 volts to pin 8 and pin 4, which is the reset and VCC pins. I'll connect ground to pin 1, which is a ground pin. I'll connect pin 6 and 7 together, and then I'll put this 0.01 microfarad capacitor to pin 5, and then to ground, just like I did with the Astable too. I'll connect this 0.01 microfarad capacitor to pin 6. I'll move this out of the way. I'll move that out of the way too. I'll connect this resistor to pin 7, which is going to be our 1 mega ohm resistor, and then I'll connect the capacitor to ground and the resistor to 5 volts. I'll connect the LED to the output, which is pin 3, connect the 220 ohm current limiting resistor, and then connect that to ground. Now I also got to hook up this switch, so I'll connect up ground to the input of the button. I'm going to need another resistor actually to tie the button so it's normally high unless it's being pushed. Don't know why I have 2 there. And then I'll just connect the output of that to pin 2. And last time I forgot to add a 0.01 microfarad capacitor in between power and ground just to smooth things out a bit, so I'll add that now. And yeah, that's a full schematic on Easy EDA. So thanks for watching.